Okay, we should be live now.
Yeah, I've just got the message. So we'll just give everyone a chance to join, and then we'll commence. I can see a number of people joining, so that's great.
That shows that it's working.
It's still just a minute before 5, so we'll give people at least 1 or 2 minutes, Jessica, to join us.
Yep, no problem.
I can see the participants ticking up as we speak. So those of you who have joined us, we're just giving others a minute or so to just log in so that they don't miss the start. Okay. Hi everyone, welcome to this Forrest Fellows and Scholars webinar. I'm Tim Coleman, I'm the Deputy Vice Chancellor Research here at UWA, and today's speaker is Jessica Buck. Just like to acknowledge that the university is situated on Noongar land, and the Noongar people remain the spiritual and cultural custodians of their land and continue to practice their values, languages, beliefs and knowledge. As I mentioned, today we're really fortunate to have Jessica Buck as our speaker. She's a Forrest Fellow. She's at the UWA Centre for Child Health Research and Telethon Kids Institute. Jessica is a 2020 Forrest Fellow in the Brain Tumour Research Program at TKI and collaborating also with UWA. Her current research covers a range of topics as related to finding more effective treatments and less side effects for children with brain cancer. We were really pleased that Jessica joined TKI and UWA after her PhD and also her MSc at the University of Oxford. So she comes with a fantastic track record, and she's building further on that here during her Forrest Fellowship. So Jessica will present her talk, and then please, if you have questions, you can start adding them to the Q&A text box. So please do use the Q&A function. And then after the presentation, Jessica will be really pleased to engage you with those questions and answers. So Jessica, over to you for your talk, Developing Better Treatments for Kids with Brain Cancer. Thank you.
Thanks very much. I'm just going to be really unprofessional and get up and wave my arms around because the lights have just turned off on me in this room. There we go, that's much better.
We can see you.
Too. Okay, well, thank you very much for having me. I'm really excited to present this talk. I'd also like to encourage everyone to add any of their questions as we go through. And I'm trying to keep this as simple as possible, but I do tend to use a lot of scientific words. So if there is anything that you don't understand, please do type it into the Q&A and we'll get to it at the end. And I know that there's a range of backgrounds from people who are watching this talk, so there's definitely no such thing as a silly question. I'm really interested to hear what you guys are interested in. So please do ask as many questions as you like. So I just wanted to introduce to you our team. This is the brain tumour research team at the Telethon Kids Institute. So here we've got our co-head of the lab, Dr. Nick Gattado. Nick is a clinician and he's head of the Paediatric Oncology and Haematology Department at the Perth Children's Hospital, which is where our labs are based. And this is Dr. Raylene Endersby. She is a scientist, and together with Dr. Nick, she co-heads the lab. And so it's a really great team that they have, because we have both the clinical aspects and we also have the scientific aspects, and we work together to make sure that all of the science that comes out of our lab is directly relevant to patients in the clinic. So we've got quite a large team. We've got a few post-PhD researchers like myself. We have research assistants and PhD, masters and honours students, as well as some undergraduate volunteers. So a really nice, big and diverse team. So I'm going to start with a little bit of background about cancer in children and in adults. So the types of cancers that children get are different. Brain and central nervous system tumours, which is basically the brain and the spinal cord, those tumours are much more common in children than they are in adults. So in adults, the cancers that are common that you might be familiar with, they include prostate cancer, breast cancer, lung cancer, melanoma, but brain cancer in adults is much less common. In children, there is a number of different cancers. Leukemia is the most common of these and probably one that you've heard of, but brain tumours make up 1/4 of all cancers in children. They are thankfully very rare, but as a percentage, quite common. Now, there's been a lot of really good research done in childhood cancer, particularly in leukemia. So if we have a look at data from the last 30 years, you'll see that survival has improved from around 70% to now it's above 85%, and I think the most recent data is even above 90%. So there's been so much research done in this space that we've had really great improvements in survival from leukemia. And the same can be seen in other common cancers, including lymphoma and neuroblastoma. But when we look at brain tumours, sadly, there's been no improvement in the last 30 years. And that's something that our team and a lot of others around the world are really trying hard to fix. So now I'm going to tell you about some of the types of childhood brain tumours. And you might notice here that I've switched from talking about cancer to talking about tumours. And I just want to make that distinction. A tumour is anything that's growing in the brain that shouldn't be. Some of these tumours are benign, which is a word you might have heard of. And that means that they're not very aggressive and they're typically not very dangerous. They can just be monitored or removed by surgery and they won't come back. And these ones typically don't need heavy treatment like chemotherapy. Brain cancer, on the other hand, is aggressive and it requires treatment. So some of the brain cancer types include glioma, medulloblastoma, and ependymoma. Okay, whereas some of the tumours that are often more benign include craniopharyngioma and things like that. So there's a lot of different types of brain tumours. Not all of them are very aggressive, not all of them are very dangerous. But our work focuses on the ones that are. So our lab studies a few different types of childhood brain cancer. We don't study adult brain cancer actually. Those cancers are very different, both in the way they develop and the way that they're treated. And so we stick to childhood brain cancer. So we focus on 4 main types. Medulloblastoma is the most common paediatric brain tumour, so the most common brain tumour in children. Ependymoma is the second most common, and it has a pretty poor survival rate. About 50 or 60% of kids will still be alive at 5 years after their diagnosis. Another type that we work on is called pineoblastoma, and it's a very rare tumour, extremely rare actually, but it has also a fairly low survival rate. And the last one that the brain tumour team works on, in collaboration with Terry Johns in the Oncogenic Signalling Lab at Telethon Kids, is a tumour called DIPG, or now more formerly known as diffuse midline glioma. And this tumour is really one of the nasty ones. It has a 0% survival rate. Sadly, most children who are diagnosed with DIPG will pass away within 2 years. There's no known treatments. Radiotherapy helps to ease the symptoms, to give the kids a bit more time with their family, but there are no treatments that provide a cure for this disease. So all of these tumours are very important to study, and it's very important that we find more effective and less toxic treatments for all of these kids. So today my talk's going to focus on medulloblastoma. That's the primary type of cancer that my lab works on. And just to keep it simple, I'm just going to focus on this for today. So medulloblastoma is a tumour of the brain, in particular a part called the cerebellum. So this bit here is what an adult cerebellum looks like. It's mine actually, from when I had when I worked in MRI research. So this is my brain. This is the major part of the brain up here, the wrinkly cortex that kind of everyone's familiar with from photos. But then we've got this little bit of cerebellum down here. And it's got this really kind of leafy branched structure. And what the cerebellum is responsible for is balance and coordination. So one of the things that, one of the symptoms that kids with medulloblastoma will get is they become uncoordinated and it's hard for them to balance. And that's a really minor symptom, especially when you're thinking of kids that are, 2 or 3 years old and they're probably pretty uncoordinated to begin with. And so part of the problem with this disease is that the symptoms are so mild to start off with until these tumours are really quite bad. And so it's very hard to diagnose them without a brain scan. So that's what a normal cerebellum looks like. And this is a child with a medulloblastoma tumour. So you can see the tumour here has basically grown throughout the entire cerebellum. And another effect that you can see, this is a medical term, this is called hydrocephalus. And this occurs when the tumour blocks the flow of what we call cerebrospinal fluid. And that's kind of it's similar to blood in that it contains oxygen and nutrients, but it's the fluid that bathes the brain. So your brain's kind of floating around in this sack full of fluid. And when it blocks the path, when the tumour blocks the path of the fluid, this bit swells up, and that also causes symptoms like headaches and nausea. And so that's how most brain tumours are diagnosed when kids come in with, really non-specific symptoms like headaches and vomiting and a little bit of clumsiness. Another feature of medulloblastoma is that it's really quite aggressive. And what tends to happen is that the tumour spreads from this main site here in the cerebellum, goes all the way down the spinal cord and into your spine. And so for that reason, when we treat this tumour, we not only need to treat the whole brain to make sure there's no little tumour cells floating around in here, but we also need to treat the entire spinal cord. And that's a unique feature of medulloblastoma, and it's responsible for some of the side effects that we do see with treatment that I'll go into in a minute. So medulloblastoma has a lot of different types. So 20 years ago, 10 years ago, the way that medulloblastoma was distinguished was a sample of the tumour would be taken during surgery to remove it, and the pathologist would have a look at it under the microscope. And these are some of the different types you could see, so based on the cellular features. So this one, for instance, has large cells, whereas this one has a feature that we call nodularity, which is these little circles. And these different types of different looking cells, they kind of gave some clinical information as to how severe the disease would be, but they didn't really predict very well which kids were going to do well and which kids weren't. And so there's been a lot of really, really great research done in the last 10 years to come up with this. Now, this is a very complicated chart, and I'm not going to go into it, but suffice to say that a lot of scientists have looked at the genetics that make up these tumours, and they've divided it into all of these different subgroups. So some are more likely to occur in infants, some in actually young adults, But the thing I want you to focus on is that there's 4 main types. We've got Wnt in blue, Sonic Hedgehog in red. Yes, that is the actual name of a protein. A scientist named it. And that's one of the key drivers of this type of tumour. And then we've got group 3 and group 4, because we haven't quite figured out what drives those just yet. So they're the main subtypes. And then we've got all of this different genetic information that underlies all of those. And so that's been really, really helpful in working out which kids are going to do better and which kids might do worse. So now I'm going to tell you about the treatment for medulloblastoma. So the first line of treatment is surgery. And when the surgeon goes in, they're aiming to remove as much of the tumour as they can. But you've also got to be careful with the normal brain surrounding the tumour, especially because these are young kids. What happens after the surgery is that kids are sent for radiation therapy or radiotherapy. So only kids over the age of 3 years old can receive radiotherapy, because for toddlers it's really too damaging for their brains. Following radiotherapy, then these kids get chemotherapy, and this is multiple doses and multiple rounds. So it's a huge amount of treatment for these little kids. And so I'll just go into this in a little bit more detail. So radiotherapy has to treat the entire brain and the spinal cord, because of what I said earlier about these medulloblastoma cells. They like to escape and find other places to live in the nervous system. And so to design a treatment that just treats these areas while not treating, the rest of the body, because we don't want to blast everywhere with radiation, it involves this really complicated plan of different beams, and there's a lot of different experts involved in planning these treatments. And for our research, we're lucky here in Western Australia that we have the first mouse-sized radiotherapy machine in the Southern Hemisphere. So I'm going to tell you a little bit about our research that we've done with it, but it's a really cool piece of equipment that allows us to do some really world-class research here at Telethon Kids and UWA. So after radiotherapy, these kids get chemotherapy. And this is a really heavy schedule, using 3 different drugs. This chemotherapy is actually much more severe than what an adult would go through, whether that's an adult with brain cancer or an adult with lung cancer. These chemotherapies are so severe that after each cycle, so each 2-week block, they actually need to have treatments to rescue their bone marrow, to rescue their blood cells before they can have a next round. So this is really, really severe therapy that we're throwing at these very young children. And sadly, this results in side effects. So there is a lot of them. So the radiotherapy that we give the kids, while it's absolutely necessary to cure some of these kids, it results in cognitive deficits. So these kids have trouble with school. They often need help with their reading and writing. They're actually at risk of developing other cancers that are radiation induced. Some of the radiotherapy that targets the spine actually leaks towards the heart and the lungs, and it can affect those. And the chemotherapy can also often result in hearing loss. So even in the kids that survive their treatment for brain cancer, there is a whole range of side effects. And so that's what my lab's working really hard to work on, is finding treatments that not only allow a greater proportion of kids to survive their disease, but also to survive with a better quality of life. And so now I'm just going to take you back to those 4 molecular subgroups of medulloblastoma that we saw earlier. Wnt, Sonic Hedgehog, group 3 and group 4. The reason these are really important is because they predict how well a child is going to do with standard treatment. So this is a survival curve. Every time the curve dips down, that's a death. So you can see with this blue line in the Wnt subgroup, more than 95% of children are surviving. So this subgroup has really great outcomes. Now, if we look at group 3, by 5 years after diagnosis, only around 30% of children are still alive. So this group 3 subgroup has a really poor prognosis. And as a result, that's the subgroup that my lab is focusing on at the moment. We're focusing on finding better treatments for this group 3 subtype so that we can help these kids survive their disease. So as I said, my lab is trying to develop better, more effective, but also less toxic treatments for kids with medulloblastoma, especially this group 3 subtype. And so the way that our lab tries to do this is we start with the patient. Patients that have surgery to remove their tumour, after the pathologist has done their thing, often there's a little bit of tumour left. And so if the patients and their families agree to it, we take those tumour samples and we take those brain cancer cells and we try to grow them in a number of different ways. And that way we can test new therapies on them. So we've got a whole, it's called a biobank, a whole series of patient samples that we've collected over the years that we can use to test, we can test new drugs. We can test whether we can use new cancer therapies that are called immunotherapies, which use the immune system to fight the cancer. We can also test the effect of radiation and radiotherapy on these tumour cells. So the first thing we do is we'll test the cells, we'll test new therapies, whatever we've thought of. We'll test them on cancer cells that are growing in a dish. This is the quickest and easiest way to do it, but there's a lot of drawbacks to this in that probably less than 1% of things that will kill cancer cells in a dish are actually going to work in humans. So the next thing we do is called preclinical testing, where we grow these patient-derived tumour cells in preclinical models, and then we test our new drugs or our new radiotherapy treatments in these preclinical models. And then these are much more representative of what will happen, what the response will be in a child. So from there, we can use that data to design new clinical trials for kids with brain cancer, so that hopefully we can then get better outcomes for patients. And then hopefully we can then use that data from these patients in our clinical trials to kind of inform the next round. So everything we do is centered around these patient samples that we get. So I'm just going to tell you about recent success that our lab has had. So we've just developed a drug called Prexasertib. And so this was a drug that was developed in the United States, and it's been tested for use in a lot of other cancers, adult cancers. But hardly any drugs that are tested in adult cancers have actually ever been trialed in childhood cancers. And the reason being that childhood cancer, especially brain cancer, is rare and therefore not profitable. And so a lot of these drugs that are used in adult cancers have simply never been tested in children. And so what our lab did was we did a drug screen where we grew some cancer cells in a dish and we tested thousands and thousands of drugs that were used in adults or were used for different diseases. And we tested which ones would actually kill these brain cancer cells. And what we found is that some of the drugs that came out as really effective worked by blocking DNA repair. And that's important because the way that, without going into too much detail, the way that radiotherapy and chemotherapy both work is they damage the DNA in cancer cells. But what happens is some cancer cells have worked out a way around this and they can actually repair the DNA, and that way they don't die or they become resistant to treatment. So the way our lab is looking at it is we're trying to make chemotherapy and radiotherapy more effective by adding in drugs that block DNA repair. So that way this time, when we have radiotherapy and when we have chemotherapy, the cancer cells can't repair that DNA damage and they actually die. And this, we hope, will lead to better survival for kids with brain cancer. And so just for the more scientifically minded of you, this is a little diagram of what this actually looks like in practice. So we did our drug screen and we got a whole heap of results from that. We selected targets based on the DNA damage repair pathway. We then tested, and this bit's really important, we tested a number of different drugs targeting the same molecule. So that's called CHEK1. CHEK1 is part of the DNA damage repair pathway. Now, there are, in existence, many, many different drugs that can target CHEK. And we wanted to be agnostic to drug company. So we actually got 4 different drugs in from a variety of different companies. And we tested all of them to make sure that we were using the best one, the best of it, the best drug in class, it's called. And that ended up being this one. It's got a long name, LY260368, but it's better known as prexasertib, because that's quite a mouthful. So we tested and we found that this one was the best in class. So then we went on and we tested what would happen if we combined this drug with chemotherapy. Because on its own, it doesn't do much. But when we add that DNA damage from the chemotherapy, and then we add the DNA repair blocker, which is the prexasertib, it works really well. And what this is showing is that in combination with chemotherapy, so cisplatin, cyclophosphamide, and gemcitabine, adding prexasertib really extended survival in our preclinical models. And so this led to a new phase 1b clinical trial, which has been running in Perth since 2019. And this trial is called SJ Elliott. It's named after little Elliot here, who was a patient from Dr. Nick. And little Elliot sadly didn't make it, but his parents wanted to fund something in his name. And so now we have this clinical trial, SJ Elliott, and it's a collaboration between St. Jude, which is a huge children's research hospital in Memphis in the United States, and a number of hospitals around Australia. And we had Bonnie, our very first patient. She was enrolled in 2019. So she was the first patient in Perth to receive these new, really exciting new therapies. So that's one of the success stories in our lab. And that's one that combines chemotherapy with new drugs. So I'm going to tell you a little bit about how we're combining radiotherapy now. So radiation therapy with new drugs. And this is what my work specializes in. So my most recent work tested a drug called veliparib. And veliparib is a type of drug called a PARP inhibitor. And it also works on blocking DNA repair. So as we saw before, similar to prexasertib, but just a slightly different molecular target. It targets the PARP enzyme. And so what veliparib does is it stops these medulloblastoma cells from repairing the DNA damage that radiation induces. So if you have a look at this bottom panel here, gamma H2AX is a marker of DNA damage. And so when you give radiotherapy and you wait 24 hours, you can see there's nothing there. There's no DNA damage left at 24 hours. If you combine radiotherapy with this DNA damage blocker, all of a sudden you've got heaps of DNA damage left over at 24 hours. And what happens is these cells then go on to die much more effectively. So we wanted to also test that as well as causing DNA damage, we wanted to check that they combine well. Because sometimes when you throw together 2 different therapies, they often work in unexpected ways. And we would never want to give a drug that would actually make outcomes worse. So it might stop radiotherapy from actually working, and we wouldn't want that. So we do test that in the dish. So what we do is we test different concentrations of our drug with different concentrations of our radiation. And we use this mathematical modeling that gives the combination a score. So does veliparib stop radiotherapy from working? Do veliparib and radiation work together? That's green. Or are they better than the sum of their parts? That would be blue. So ideally we're looking for blue, but green is also good because it means that these 2 drugs, they work together just fine. Red is where we're getting into the bad territory, where they actually work against each other, and we would never try that combination in children. So the next thing we tested, and this is still in a dish, is that veliparib in combination with radiotherapy stops these cells from growing. So if we don't treat the cells, we get a number of colonies forming. So a number of little tiny tumours that grow in a dish, about 250 of them. If we add radiotherapy alone, we only get about 100 colonies forming. But if we combine radiotherapy with veliparib, we get hardly any colonies forming at all, so hardly any mini tumours growing in these dishes. And that's a pretty good result, to go from radiation alone to the combination and get this huge reduction in the tumours that are growing in a dish. So that was really exciting. And so then we moved on to our preclinical testing. And the way we do preclinical testing is we never want to test just our new therapy, because that's not very informative. We want to test whether our new therapy is better than the standard of care. So in this case, we're talking radiotherapy. So what we need to do is we need to test a control group that doesn't receive treatment. We test in another group, which gets the drug alone. This group here in blue is standard of care, so radiotherapy, and we actually do this just the same as it would in the clinic. The mice that have tumours, they get a small dose of radiotherapy every weekday for 2 weeks, and that's exactly what would happen to kids in the clinic. So we do research here that directly mimics what happens to kids in the clinic, and that means that our research can translate directly into clinical trials, which is really important in this field. And then finally, the group that we're hoping to see works best is our new drug plus our standard of care radiotherapy. So we trial them together, and this has to do better than our standard of care alone, or it's not worth giving to children, because we wouldn't want to give them a treatment that was inferior. So we always, always, always test against the standard of care. And so this is another one of those survival curves that you saw before, where every drop down is a death. So if we don't treat these tumours, it drops off pretty quickly in red. Our drug alone in green doesn't do much, and we wouldn't expect it to, because it doesn't work unless there's actual DNA damage there to block. When we give our standard of care, our radiotherapy in blue, you get an extension of survival, and that's expected. Radiotherapy is effective in these tumours, but we can do better. And when we combine in purple our drug, veliparib, plus our standard of care, irradiation, we actually get a really nice extension of survival. And so that's a really good result. And that's really promising preclinical data that could be used. But what I'm going to give you here is a caveat, and that is, would we take veliparib forward into paediatric clinical trials? And the answer is probably not. And the reason for that is that we know that veliparib is not the best drug in its class. So there's a number of other drugs in the class of PARP inhibitors that we know actually are more effective at inhibiting PARP, so in blocking DNA repair, and actually get into the brain much better. The reason we tested veliparib and not these better drugs is that veliparib is the only drug of this class that has actually been tested in children. So if we wanted to go forward to a clinical trial today, we would have to use veliparib, but we know it's not the best option. So there's another drug in the same class called olaparib, and it actually goes better in our models, but it's never been tested in children before. So what happens at the moment is we're kind of waiting for the adult research to catch up for these drugs, veliparib and olaparib, to be tested in combination with radiotherapy in adults. Only after that happens can we start testing these drugs in children. It's really important that we don't take things straight into children, because the risk of side effects and toxicity are much greater. So we rely on the adult clinical trials first before we can do ours. So while this is a really promising result, and it's really important research to be doing, we've also got to be really, really careful about what drugs we take forward into clinical trial, because there's no way that we would want a child to be receiving anything less than the very best clinical trial we could offer. So that's something that we take very seriously, and we consult with our clinical team to make sure that anything we do in the lab not only reflects best practice in the clinic, but will also be useful to the clinical team. So maybe one day in the future, when some of these PARP inhibitor drugs have been tested in adults or in other cancers in children, then we can look at this PARP inhibitor with radiotherapy combination in a future clinical trial. So just to summarise what I've kind of told you about today, is that brain cancer kills more Australian children than any other disease. It's rare, but it's devastating. There's lots of different types of childhood brain cancer. Today I've focused on medulloblastoma, but our lab does research in a lot of different areas. And in particular, what our team does is we target DNA damage repair so that we can find better combination treatments for kids with medulloblastoma. And I'll just add as a side note that I've talked a lot about the side effects, and we do have another whole branch of our lab that looks at reducing the side effects by adding these drugs. We wouldn't want to add an extra drug on top of existing radiotherapy without knowing that it'll give less side effects. So that is something that our team also does test, but unfortunately I didn't have time to explain all of that today, but I'd be more than happy to answer any questions. So thank you very much for listening. I hope you found that interesting, and please let me know if there's anything I can explain better. Thank you.
Thank you very much, Jessica. That was really very clear and a difficult, complex topic, but also a difficult topic given the devastating effects for some kids and families. So thank you very much for sharing that. We are getting a couple of questions coming in, but just giving people a little bit of time to think. Can I just start with the question, and then we'll go to the Q&A board. When you presented that table, you said you don't look at everything because it was very complex, but the one thing I was wondering about is, because there was a gender row, and it seemed to indicate that males were more prone, or did I misinterpret that column? And could you just comment on that, please?
Yeah, definitely. So boys outweigh girls by a ratio of about 3 to 2 when in developing medulloblastoma. And in subtypes, that's definitely more pronounced than others. We're not really sure why that is at the moment. We just know that it occurs. We haven't found anything genetic that would explain it. So that's kind of one of the ongoing mysteries of this disease.
Okay, thank you. And there's a chat comment that says, thanks, Jess, very informative. And there's a question. Can you see the questions, or would you like me to read them out? The first question is that in your colony formation tests, you use DMSO, I think it was, in the control, which I think is just a solvent, but someone's asking why is it that you have DMSO in those tests?
Yeah, so I can answer that one. DMSO is just a chemical that we dissolve our drugs in. But DMSO actually has a slight protective effect against radiation. So we use it as a control to make sure that we're measuring the effect of the radiation or of the drug, rather than just accidentally measuring the effect of our DMSO. DMSO is also a little bit toxic to the cells. So even though we use it in very small concentrations, we just use that as a control to make sure that our results are as accurate as they possibly can be.
Thank you. And now second questions come in. Can you please give some examples of the types of side effects that are commonly observed when you administer both drugs and radiation therapy/chemotherapy?
Sure. So the way clinical treatment works, And I should preface this with, I am a lab scientist, I am not a doctor, so please forgive me if we do have any medics in the audience and I do get anything a little wrong. But the way clinical treatment works is that the kids will have radiotherapy first, if they're over 3 years of age. Then they have a little break to help their bodies kind of return back to normal, and then they'll have the chemotherapy. And sometimes they have a break between each cycle of the chemotherapy if they need it, so that, for instance, their blood cells can get back to normal. So we wouldn't generally give radiotherapy and chemotherapy at the same time. But in clinical trials, that's definitely something that's monitored for. The most common kind of toxicity that we see in clinical trials, when we give new drugs in combination with chemotherapy, is often we see effects on the liver, because chemotherapy, the way that the body breaks down those drugs is in the liver. And if we give a new drug on top of that, it might also affect the liver's ability to break these things down. So that's something that is monitored really, really closely in clinical trials. In radiation therapy, it's a little different. Radiation therapy often affects the blood cells. So these kids end up with anemia or low platelets, which affects the way their blood clots, and also less white blood cells, which is why kids that are having cancer treatment are really prone to infections. And so we just have to monitor those side effects really closely whenever we're doing clinical trials to make sure there's no toxicity.
Thank you. There's another question. Do the treatments your team are looking for have the potential to help patients in other tumour subgroups?
Yeah, so that's a really great question. And the short answer is yes, they do. Not only in other subtypes of medulloblastoma, but also in other childhood brain cancers. The best thing about targeting the DNA damage repair pathway is that it's common to all tumours. So all tumours that receive chemotherapy or radiotherapy, these drugs could work for that as well. So our findings, we've tested them. I've just shown you the medulloblastoma results today. We've tested them in Sonic Hedgehog group, Sonic Hedgehog medulloblastoma, which is another group that has kind of poor outcomes. We've also tested them in pediatric glioma, and we've tested them in ependymoma, and we've tested them in pineoblastoma. So prexasertib, which is the first one I spoke about that's in clinical trials now, that actually works well across a number of different tumour subtypes and a number of different pediatric brain cancers. So that's one of the cool things about the type of research that we do, is that it has the potential to help a lot of kids.
Thank you. I also have a question. When you showed that nice diagram with the loop, in terms of, with the permission of patients and parents taking the cell samples and then going through the loop and the feedback, can you just comment on, what is the quickest sort of time currently that you can sort of complete that sort of loop, and are there opportunities to make that faster in terms of that feedback to assist patients with options? Is that the goal?
Yeah, sure. So in the case of prexasertib, which was kind of one of the first things that our lab looked at when Doctors Nick and Raylene started it 10 years ago, that went into clinical trial in 2019. So that took about 9 years for that to go from just starting to look at the effect on cells in a dish all the way to a clinical trial. Can we accelerate that timeline? A little, with good research funding and a lot more bodies in the lab. That's kind of one of the main things that we have at the moment, is we don't have enough hands to do all of the experiments that we'd like to do. And that's kind of common across all research laboratories in the country. We don't have enough funding and enough staff to be able to do all of the things that are buzzing around in our heads. We all have ideas, but we can't physically do all of them. In terms of accelerating the timeline, we wouldn't want to do it by much. The way that you would do that, and this is what happens in adult cancers, is things go straight from being tested in a dish, on cancer cells growing in a dish, straight into clinical trials. The reason we don't do that in children is because brain cancers are very rare. And so it's really difficult to get a clinical trial up and running. You need to have, Australia needs to collaborate with the Pacific and the United States, for instance, to get a single clinical trial up and running. We simply don't have enough patients. Whereas a single hospital can do, for example, an adult brain cancer trial. And we also don't want to give kids anything that is any less than the very best we could offer, which is why we always, the clinicians, like the cancer doctors themselves, they insist on having preclinical models. So that's mouse testing before they'll even think about doing a clinical trial, because they want to make sure they're offering the very best to their patients. And realistically, that's the only way that we could speed it up if we skip some of those steps, but then we're skipping safety testing, and we're skipping the possibility that these drugs actually don't work. And so there's only so many ways you can speed it up without skipping really important steps.
Correct. I think you can still hear me. You seem to have frozen.
Am I back now?
Yes, you are. Thank you. So thanks for that answer. Yeah, I can see the complexities in that loop, and as you mentioned, yeah, depending on what's tested and the timelines.
Oh no, I think I've lost you as well, Tim. It looks like we may have lost Tim completely from this webinar. So if anyone else has any questions, please put them in the Q&A box or in the chat, and I'll keep an eye on that. But otherwise, thank you very much for listening. I'll hang around for a few more minutes just in case anyone's still typing. But otherwise, thank you very much, and I hope that you found that informative. Please don't hesitate. If you Google Jessica Buck UWA, you'll find my email address. So please feel free to contact me with any other questions or anything that I haven't answered today. Oh, we do have another question. How is what I'm doing different from before? So the answer to that is that what we're doing is combining standard of care with new drugs. And that's not often done. And the reason for that is it's hard. It's hard to do chemotherapy and radiotherapy in mice. And then to add on another drug on top of that, it's really, really demanding. And so that hasn't been done before a lot, especially in pediatric brain cancers. And another thing that we're doing now that we couldn't do before is the radiotherapy. So because we've got the only mouse-sized radiotherapy machine in the Southern Hemisphere, we can actually do these studies where we give really clinically relevant radiotherapy to mice and then test the effects of that. And so that's where our lab is doing really cutting edge research, is looking at the effects of radiotherapy on these brain tumors, because it was something that, couldn't really be done before. So an exciting thing that we're doing is we're actually looking at the side effects of radiotherapy. So if we give young mice radiotherapy, we can actually have a look at the effect on their brains, and we can use that to design less toxic, definitely less toxic. We can use that information to design less toxic treatments that involve radiotherapy, and that's something that we're really interesting. Okay, and so we've got another question here. How well do you think the combination treatment, so drug plus radiotherapy or chemo, would work in adults with medulloblastoma? And so the answer to that is very few adults get medulloblastoma. We sometimes get that sonic hedgehog subtype in young adults, so up to about maybe 25 or 30 years old. We've actually done a little bit of work in combination with other labs showing that prexasertib does work in combination with chemotherapy and radiotherapy in adult brain cancers, so one called glioblastoma. And another lab headed by Kerry McDonald in Sydney has actually tested veliparib, that's the other drug I was talking about, in combination with radiotherapy in adult cancers. So definitely the pathways that we're working on could be used to treat adult brain tumours. And we do have another question. So what's special about brain cancers, and is it the protection of the skull? It is not necessarily the protection of the skull that makes them difficult to treat. It's actually something called the blood-brain barrier. So unlike the rest of your body, blood can't go freely from your blood vessels, your veins and your arteries, into your brain. There's actually, think of it as a plastic tarp that separates the blood from your actual brain tissue. And this tarp has really specialized holes in it that only allow certain things through. And the idea of that is to protect your brain from infections and to make sure that really important nutrients like sugar are there in exactly the right concentrations, because your brain's really quite delicate. But what that means is that chemotherapy, for instance, chemotherapy can't get across the tarp. So most chemotherapy can't actually get in the brain very well. So that's a really big challenge when treating brain cancer, is that so many of the drugs we give just don't get into the brain at all. And so that is one of the first things that our labs test for when we're looking at new treatments. The first question is, does this drug get into the brain? And if not, no matter how effective it is at how effective that drug is at killing cancer cells in a dish, we just have to throw it out, because if it doesn't get into the brain, sadly, it's no use for brain tumours. So that is a really big challenge in both kids and in adults with brain cancer. It's a really big challenge for our research. So thank you for these questions. I'm glad to see so much interest in the work we're doing. If you do have any more questions, we do have a few minutes left, so I'm happy to hang around for a few minutes longer. If not, thank you all for coming tonight. Okay, we do have another question. Wonderful. The question is, do you think the cognitive deficits will be worse in those who are receiving the combination treatment versus those who are receiving the standalone treatment? And that is a fantastic question. It's something that we're very worried about. By throwing extra drugs in, do we make these treatments extra damaging? The short answer is we don't know yet, but that is something that we're testing. So before, when I talked about how we're testing radiotherapy and the effects of radiotherapy on the developing brain in mice, once we have the results from those experiments, what we're planning to do is that any new drug that we're planning on testing in clinical trials, before we go to clinical trials, we want to test the effect of that drug on the developing brain and make sure it's not worse than what we're currently using. The other main thing that we would really like to do is that we know that radiotherapy is the most damaging thing for the brain, but it's also really necessary for treatment. You can't reduce the dose of radiotherapy without having worse survival in these kids, and that's been tested before. So what we're trying to do is we're trying to add, for example, our drug with maybe half the dose of radiotherapy. Because our drugs make radiotherapy more effective, we're hoping that we can actually reduce the dose of radiotherapy that we could give to these kids. And that won't affect their outcomes, but hopefully that will affect the amount of side effects that they get. So that's something that our lab is actively working on, is how we can reduce the dose of radiotherapy to reduce those side effects. Okay, and another awesome question.
Sorry that I was lost.
Oh, no problem, Tim.
Sorry, I just dropped out. So sorry, the connection was a problem here. It's great that you were still going. Keep going,
No
thank you.
Okay, so we've got one more question here. How does the youth of the brain change its sensitivity to treatment and improve potential recovery? So again, that's a really, really interesting question. When kids are young, their brains are still developing. So all of the brain cells, most of the brain cells are there, but what they're doing is they're making connections. So with their learning, all of the brain cells are making different connections to different areas of the brain. And any treatment we give to kids when they're young, especially radiotherapy, will damage those connections. By the time you're my age, your brain's made all of the connections it's basically ever going to do. And radiotherapy is far less damaging when given as an adult for that reason. You can see, but the flip side of that coin is that kids, when they have surgery or when they have radiotherapy, they're actually quite adaptable if they suffer some damage to their brains. So kids can often relearn those skills that have been lost. Whereas if you think of an adult who's had a stroke, for instance, they'll find it really, really difficult to relearn speech or to relearn how to walk, because that adult brain, especially in the elderly, is no longer making those new connections. So while the treatment is most damaging in kids, they've also got the best potential for recovery. So yeah, it is a difficult one.
I'm sorry I missed out on hearing some of those questions. I don't know what happened to the internet. So I was just going to comment on the importance of collaboration, which was clear from your presentation, but then also in one of the other answers you mentioned the fact that with these rare brain cancers that collaboration is really essential in terms of being able to have a statistically valid analysis of treatment. So thanks for explaining that. And I guess it's just fantastic to see that collaboration, because it's just important to enable those outcomes for children which are all around the world, and that then benefits children here in Perth. Did you want to say briefly anything more about that, or do you think that sort of summarises the importance of that collaboration?
Yeah, I mean, that does summarise the importance. I mean, we work really, really closely, in particular with St. Jude, which is kind of one of the biggest children's hospitals in the US. That's where both Dr. Nick and Dr. Raylene did their training. We also work really closely with labs around Australia and hospitals around Australia. So for example, in Sydney and in Melbourne, we work really closely with them. In Europe, we have a number of collaborators in Germany and the UK. And one of the best things about childhood cancer research, as opposed to kind of adult cancer research, is that everyone wants the same thing. And so it's a lot more collaborative than, so I started out in adult brain cancer research, and that environment was a lot more competitive, whereas this is everyone's trying to reach the same goal. So everyone's happy to share their samples and to share their data and to say, oh, we've already tried this and it doesn't work. So just so you guys know, don't waste your time and money and effort on this. And so that's really good, because it means that everybody around the world is kind of working together towards better outcomes. And that's really great.
Okay, thanks, Jess. And there's one final question, and then I think we'll wrap up, which you can see the question, so I'll let you go.
Sure. So how well do you think the combination treatment can help for those with glioblastoma? And the answer is, I think it can do pretty well. So we've actually trialed this in our lab in glioblastoma. We've trialed prexasertib in combination with chemotherapy and radiotherapy, and it was more effective than just the chemotherapy or the radiotherapy alone. We've also tried, our collaborator, Dr. Kerry McDonald from Sydney, has trialed veliparib, which is the PARP inhibitor I was telling you about. She's trialed that in combination with both chemotherapy and radiotherapy. And again, that combination was much more effective than the drug alone. And so I think in glioblastoma, veliparib plus radiotherapy is actually already in clinical trial. So that's the adult brain cancer.
Okay, thank you. So we've just reached the hour. So I'd just like to finish by saying that it was nice also, Jess, to see Buck et al. 2021 on the slide. So clearly you're publishing this work and sharing this knowledge with other scientists, and that's a great outcome. And I'd just like to thank you on behalf of everyone for such a great seminar and such an important topic once again. And thank you very much. So thank you very much. Yes.
No worries. Thanks very much for having me.
And thanks everyone for joining us.
Yeah, thanks to all the participants for their wonderful questions. It's really great when people actually have things to ask. So thank you very much.
Okay. Thanks everyone. Bye-bye.